Section: Introduction. In this section, we discuss how inference efficiency is becoming crucial in AI, especially as we consider the limitations of token-by-token decoding, which restricts parallel processing. During this decoding process, we use multi-head attention (MHA) to store the key value states of previous tokens. However, these cached states grow linearly with both batch size and sequence length, quickly consuming high bandwidth memory. The time taken to retrieve this large cache from off-chip memory often overshadows the actual computations we perform at each decoding step, leading to increased latency and underutilization of GPU resources. This issue affects various applications, including interactive systems, large language model agents, and high-throughput inference tasks. To address these challenges, we recognize the need for a more efficient redesign of attention mechanisms. An ideal solution should maintain high model quality, scale well across devices, and effectively use modern hardware during inference. We explore several inference-aware attention variants that speed up decoding. For instance, multi-query attention (MQA) reduces memory usage by caching only one key value head, while grouped query attention (GQA) shares key value heads among smaller groups of query heads to improve quality. Additionally, multi-head latent attention (MLA) compresses the hidden state into a single latent vector, which helps reduce memory demands. However, we note that the computational power of modern accelerators has outpaced memory bandwidth growth. We use arithmetic intensity, which measures the ratio of operations to memory access, to evaluate whether a workload is limited by memory or computation. MQA increases arithmetic intensity by reusing a single key value head, which reduces memory footprint and reload time, but at the cost of quality and parallelism. GQA improves arithmetic intensity slightly but still requires significant memory for large group sizes. In our work, we aim to redesign attention variants with a focus on arithmetic intensity and scaling during decoding while maintaining model quality. We define the group size as the number of query heads per key value head, which influences arithmetic intensity. Increasing this group size enhances arithmetic intensity and reduces the key value cache size, but beyond a certain point, it can hinder parallelization and GPU utilization. Guided by these principles, we propose two new attention variants that balance high arithmetic intensity with efficient scaling. We implement low-level optimizations to ensure our kernels can overlap computation with memory access, keeping tensor cores fully utilized. Our first variant, Grouped Tied Attention (GTA), combines key and value representations into a shared state for small groups of query heads, significantly reducing the key value cache size and improving arithmetic intensity. Our second variant, Grouped Latent Attention (GLA), extends latent attention in a way that is friendly to parallel processing, achieving similar quality to MLA while being faster, especially in scenarios with longer query sequences. We demonstrate the effectiveness of these variants through experiments on moderate-scale language modeling, showing improved performance metrics compared to existing methods. We also release our optimized kernels as open source to support further research and practical applications. Section Summary. In this section, we highlight the challenges of memory-bound performance in multi-head attention (MHA) during decoding and propose two hardware-efficient attention variants, Grouped Tied Attention (GTA) and Grouped Latent Attention (GLA), which improve arithmetic intensity and reduce latency while maintaining model quality. Our optimizations lead to attention decoding kernels that are 1.2 to 2 times faster than existing methods, and we release these kernels as open source to support further research and application. Section: Preliminaries. In this section, we discuss the foundational concepts of our approach. We introduce inference-aware attention, where MQA minimizes the size of the key value cache in multi-head attention, speeding up decoding. However, this method compromises model quality, as each device must duplicate the single key value head during distributed inference, negating memory savings. To tackle this, GQA groups query heads to share a unique key value head, significantly reducing duplication across GPUs without additional memory costs. This method decreases the key value cache size compared to standard multi-head attention while enhancing model quality over MQA. We find that to maintain quality, a moderate number of groups is necessary, but this can lead to the key value cache exceeding high bandwidth memory capacity when using only a few devices, such as with a tensor parallelism degree of 2. We also explore multi-head latent attention, MLA, which compresses each token's hidden state into a low-rank latent vector, caching only this vector and projecting it back to full head keys and values. This design further reduces memory usage by caching a single low-rank representation for both keys and values. During decoding, the projections for keys and values are integrated into the query and output matrices, meaning explicit keys or values are never created. Each query directly interacts with the latent vector. MLA maintains positional information by adding a small separate rotary position encoding to the latent vector, allowing for efficient weight absorption. Next, we address distributed inference, where sequential decoding limits parallelization to the head axis of the attention component. Tensor parallelism partitions attention layers across devices, requiring frequent synchronization of activations. This overhead is lessened by fast GPU interconnects like NVLink. Tensor parallelism avoids the need to replicate the entire model on each GPU, unlike data parallelism, which is impractical for large models. It also prevents idle GPUs during token-by-token decoding, a drawback of pipeline parallelism. We prefer tensor parallelism during decoding as it spreads weights across GPUs, alleviating the bottleneck of loading the key value cache when processing tokens individually. We then provide an overview of GPU architecture, noting that modern GPUs have numerous compute elements organized into streaming multiprocessors, along with a memory hierarchy that includes high-bandwidth memory and on-chip shared memory. For instance, the NVIDIA H100 GPU features 80 GB of high-bandwidth memory and specialized tensor cores for efficient matrix multiplications. In terms of performance, we classify operations as compute-bound or memory-bound based on their arithmetic intensity, which is the ratio of arithmetic operations to memory accessed. An operation is compute-bound if it is primarily limited by arithmetic operations, while it is memory-bound if memory access time dominates. Our methodology focuses on designing hardware-efficient attention variants by maximizing arithmetic intensity and efficiently parallelizing across devices by linking key and value states and sharding the cached latent representation. During sequential decoding, we observe that the large general matrix multiplication workload shifts to smaller batched general matrix vector multiplication. Each element of the cached key matrix performs one multiply accumulate operation with the query element, resulting in a low arithmetic intensity that is far below the potential of the GPU. This low utilization indicates a significant gap between the compute capabilities of modern GPUs and their memory bandwidth. To address bandwidth limitations and enhance arithmetic intensity during decoding, we can fuse kernels, optimize data tiling for on-chip reuse, selectively recompute small intermediate results, or use specialized attention reordering to minimize off-chip transfers, all without changing the attention design. Section Summary. In this section, we discuss how GQA improves model quality and reduces KV cache size by grouping query heads to share distinct KV heads, addressing the limitations of MQA. We also highlight the importance of maximizing arithmetic intensity in decoding to enhance GPU utilization, as current methods often lead to underutilization due to the disparity between compute throughput and memory bandwidth. Section: Design Strategies for Maximizing Arithmetic Intensity. In this section, we discuss design strategies aimed at maximizing arithmetic intensity. We introduce GQA, a general attention method that utilizes one loaded key value, KV, head for each group of query heads. While sharing the KV head does not decrease the number of operations, since each query head still calculates its attention scores, it does lower memory reads, which in turn increases arithmetic intensity in proportion to the group size or the number of queries per distinct KV head. For instance, in MQA, which uses a single KV head for all query heads, the arithmetic intensity is roughly equal to the number of query heads. DeepSeek has proposed MLA, which focuses on inference and uses low-rank matrices to avoid creating KV states, thus achieving high arithmetic intensity through three main strategies: caching a single latent head, reusing this latent for both key and value, and employing many query heads. Initially, MLA loads one latent head and reuses it across all query heads, similar to MQA. This representation, stored in on-chip memory, serves both key and value states during attention computation, effectively doubling the arithmetic intensity compared to the most advanced MQA designs. Although DeepSeek does not explicitly mention it, using low-rank projections to reduce the number of parameters in the latent cache allows for increasing the column dimension of the up projection matrices to recover those lost parameters. This means we could use the saved parameter budget to add more query heads, maintaining model capacity and enhancing arithmetic intensity during decoding by sharing a single latent head across more query heads. Our findings indicate that arithmetic intensity is influenced by the number of query heads, and generally, increasing the group size reduces the KV cache size while boosting arithmetic intensity, thereby maximizing GPU utilization. We denote the multiplicity of KV as either 1 or 2, where 1 indicates shared states and 2 indicates distinct states. Unlike increasing the group size, raising the multiplicity from 1 to 2 increases the KV cache and decreases arithmetic intensity. We also note that increasing arithmetic intensity through a larger group size comes with a trade-off in parallelization capability. If the group size becomes too large relative to the number of devices, it leads to parameter duplication and diminishes parallelization benefits. For zero redundancy parallelism, the number of KV heads should be at least equal to the number of devices and at most equal to the number of query heads. In practice, the duplication factor indicates how many copies of the KV heads exist across the devices. We establish a zero redundancy bound, where the group size must be less than or equal to the number of query heads divided by the number of devices. We also explore group-tied attention, GTA, which builds on GQA's design. Singular value plots show that the key cache has a steep decay, indicating that keys are highly redundant and reside in a low-rank subspace. We find that applying rope to only a portion of the head dimension preserves accuracy, suggesting that we can rotate just a slice of the head dimension needed for positional encoding. This allows us to share or tie the remaining unrotated channels with the value states. In GTA, each group of query heads shares one distinct KV head, and we further tie the key and value projection parameters to create a single state. This tied KV state matches the shape of an individual key or value vector. The value path utilizes the full dimensionality of the tied KV state, while the key path reuses only its first half. The remaining rope component comes from a separate one-head projection of the hidden state, which is broadcast across all groups. Our empirical tests show that applying rope to the shared half can degrade quality, so we avoid rotating the tied portion. After these adjustments, we define the query, key, and value states. By tying the KV states, we load a single state into memory, reuse it for both keys and values, and share it across a small set of query heads. This approach reduces memory transfers, roughly doubles the arithmetic intensity, and halves the KV cache size compared to GQA with the same number of groups. Our experiments indicate that performance metrics remain comparable to those of GQA. Section Summary. In this section, we explore design strategies to enhance arithmetic intensity in attention mechanisms by reusing key value KV heads across query heads, which reduces memory reads without increasing operations. We introduce group-tied attention, GTA, which further optimizes memory usage and performance by tying KV states and partially applying positional encoding, resulting in a significant reduction in KV cache size while maintaining model quality. Section: Grouped Latent Attention, GLA. In this section, we introduce Grouped Latent Attention, GLA. We note that the low-rank key-value joint compression in MLA caches a single latent head for each token, with a specific dimension. Due to tensor parallelism, the key and value projections are divided across devices, requiring each device to hold the entire latent to reconstruct the keys and values. This results in duplicated latent key value caches across devices, increasing the overall cache size with more ranks. In comparison, GQA stores more elements per token, leading to a larger cache than MLA under certain conditions. However, in a 4-degree tensor parallel setup, both MLA and GQA8 have similar cache sizes per device, although GQA8 uses significantly more memory for its cache. We find that while MLA achieves high arithmetic intensity, sharing the latent across heads limits the efficiency of parallel processing. To address this, we propose GLA, which compresses tokens into fewer latent heads, each with a smaller dimension. During training, each latent head creates unique key and value features for its group of query heads. This design allows for efficient distributed scaling without duplicating the latent cache. For example, with 2 latent heads, GLA maintains the same cache size as MLA but reduces the cache per device when the tensor parallelism is 2 or more. In our experiments, we set the number of latent heads to 2, matching MLA's cache size while having the cache footprint per device. This smaller cache also enables us to adjust the distribution of processing across devices, improving performance. We observe that GLA achieves a higher arithmetic intensity compared to GQA and maintains good model quality. Additionally, we discuss system optimizations for achieving peak performance on modern hardware, emphasizing the importance of efficient memory loading and processing to keep the specialized matrix multiplication units active. Section Summary. In this section, we propose Grouped Latent Attention, GLA, which compresses tokens into fewer latent heads to reduce the KV cache footprint per device while maintaining high arithmetic intensity and model quality. GLA efficiently partitions query heads across tensor parallel ranks, enabling better distributed scaling and reducing memory load imbalances compared to the existing MLA approach. Section: Asynchrony with Software Pipelining and Warp Specialization. In this section, we discuss 2 techniques we use to overlap computation and memory loading: software pipelining and warp specialization. With software pipelining, we load the next key value, KV, block while the current one is still being processed, preventing the tensor cores from idling. Warp specialization involves having different warps for memory loading and matrix multiplication. Some warps handle memory loading using either the tensor memory accelerator or asynchronous copy instructions, while others focus on matrix multiply accumulate operations. This separation simplifies our software pipelining, allowing the warp scheduler to efficiently manage both tasks. Next, we address the distributed offset calculation for paged KV. As new attention models like MLA, GTA, and GLA demand more from both computation and memory, we need to load memory as quickly as possible. Paged KV is a common method for storing the KV cache, but it complicates the use of the tensor memory accelerator, which is designed for efficient address calculations. Instead, we utilize asynchronous copy instructions, where each thread issues its own load commands. Address computation can be costly, so we have multiple threads within the same warp work together to calculate addresses. For instance, to load a block of size 128 by 128 from global memory to shared memory, we use 128 threads, grouping them into 8 groups of 16. Each group loads specific rows, and threads within the group share the global memory address to load the KV cache elements efficiently. This method allows us to handle various page sizes without significant slowdowns, even with a page size of 1, which is beneficial for applications like prefix caching with radix attention. We benchmarked the speed of paged KV with GLA, achieving a speedup of 1.2 to 1.5 times. In our experiments, we validate that our methods, GTA and GLA, provide quality comparable to GQA and MLA, are easily parallelizable, and run efficiently on modern hardware like the H100 GPU. For example, GLA matches the quality of MLA while being easier to shard, and our GLA kernel is up to twice as fast as DeepSeek Flash MLA in a speculative decoding setup. We also explore a variant, GLA_Q, where the query latent is sharded to reduce duplication and parameter count per device, although we mainly include this for ablation since the query latent is not cached. For our experimental setup, we train models at 4 scales: small, 183 million parameters; medium, 433 million; large, 876 million; and XL, 1.471 billion parameters, using the Fine Web Edu 100B dataset and following the GPT-3 model configuration with the Llama 3 architecture. The small model is trained on 25 billion tokens, while the others are trained on 50 billion tokens each. Additional details on architecture and training setup can be found in the appendix. We report validation perplexity on 100 million tokens from the Fine Web Edu validation set and evaluate additional datasets, including Wikipedia and C4, each also using 100 million tokens. We present the average perplexity across these datasets in our tables. For both MLA and GLA in the large model, we typically use a rope dimension of 32, with further results for a dimension of 48 in the appendix. GLA2 generally outperforms MLA at medium and large scales, achieving lower validation perplexities while performing comparably in the small model. Notably, GTA addresses limitations of GQA, further reducing perplexity in medium and large models. GLA2 and GLA_Q2 show similar performance in the large model, achieving the lowest average perplexities compared to other variants. GTA effectively reduces the KV cache per device in lower TP degree settings. In the XL model, GTA4 slightly outperforms GQA4 in perplexity, while GLA maintains an edge over MLA. Section Summary. In this section, we describe our techniques for optimizing compute and memory loading through software pipelining and warp specialization, which enhance efficiency in processing paged key value (KV) caches. We also present experimental results demonstrating that our methods, GTA and GLA, achieve competitive quality and performance on modern hardware, with GLA showing significant speed improvements and lower validation perplexities compared to existing models. Section: Downstream Evaluation. In this section, we evaluated the zero-shot performance of our model on various standard benchmarks, including SciQ, OpenBookQA, ArcEasy, HellaSwag, PIQA, Wino Grande, and MMLU. Our attention variance either maintained or improved upon baseline accuracy across these benchmarks. For the medium model with 433 million parameters, GLA2 achieved the highest average accuracy of 55.4%, slightly surpassing MLA's 54.9%. In the large model with 876 million parameters, GLA2 reached an average accuracy of 57.5%, just 0.1 points below GTA4 and effectively matching GQA4, showing that our grouping method does not compromise quality. This trend continued with the 1.471 billion parameter XL model, where GLA2 attained an average accuracy of 60.0%, compared to MLA's 59.1%, while both GTA4 and GQA4 scored 60.2%. These findings confirm that our hardware-efficient variants maintain or enhance performance from medium to XL sizes. For further details on our evaluations, we refer to the appendix. Regarding parallelization, we designed GLA to scale across GPUs by dividing latent heads, which reduces memory traffic and speeds up decoding. In contrast, MLA uses tensor parallelism by duplicating its single latent head across GPUs, which can be costly. Earlier systems often resorted to a mix of tensor and data parallelism, assigning different batch sequences to separate GPUs, which is beneficial for large batches or high request volumes. We tested GLA's scalability using DeepSeek Coder v2 base, which has 236 billion parameters, quantized to FP8, and served with our Flash Attention 3 kernels. Our experiments compared pure tensor parallelism on 8H100 GPS with a hybrid approach that included two-way or four-way data parallelism. In the hybrid setup, only the attention module is replicated across data parallel groups, and its outputs are combined before the feed-forward layer to avoid duplicating the key value cache. GLA configurations with zero redundancy sharding outperformed MLA in similar parallel setups because they accessed a smaller key value cache per device. For instance, with 64 concurrent requests, GLA8 on 8 GPUs delivered up to twice the throughput of the single-head latent MLA. This advantage continued under hybrid parallelism, where GLA8 outperformed MLA even when both used similar setups. GLA8 with pure tensor parallelism also surpassed MLA using hybrid methods. Our design for GLA enhances peak throughput and remains effective under heavy loads. Real-world workloads often have imbalanced sequence lengths or small batches, which can cause delays. In a mixed sequence load with 4 concurrent sequences, GLA8 achieved about 2.5 times the throughput of MLA. GLA4 also exceeded MLA's performance and showed greater tolerance for workload imbalances. In another test with 16 concurrent requests, GLA8 achieved higher throughput than MLA under hybrid parallelism. Overall, GLA matched or exceeded MLA's performance in both pure and hybrid parallel setups with smaller data parallel ranks, demonstrating its robustness against workload imbalances. For more detailed results on latency, throughput, and benchmarking, we refer to the appendix. Lastly, we benchmarked the decoding kernels for MLA and GLA. Our GLA implementation, which uses 2 latent heads of 256 dimensions each, is about 20% faster than the optimized MLA implementation, Flash MLA, in standard decoding and over twice as fast in speculative decoding. Our GLA kernel utilizes up to 93% of the maximum memory bandwidth and 70% of the maximum TFLOPS on the H100 GPU, effectively maximizing both memory and compute resources. Section Summary. In this section, we evaluated the zero-shot performance of our proposed attention variants across several benchmarks, finding that GLA2 consistently retains or exceeds baseline accuracy, achieving up to 60.0% on the largest model scale. Additionally, we demonstrated that our GLA architecture scales efficiently across GPUs, significantly improving throughput compared to MLA, especially under varying workload conditions. Section Discussion. In this section, we discuss related work, limitations, and future directions. We review attention mechanisms that minimize the KV cache during pre-training, explore broader hardware-efficient designs, and look into strategies for faster decoding of large language models, LLMs. We also examine the application of partial rope and low-rank projections, which influenced our methods. Our approach, GTA, reduces the unsharded KV cache size by about half compared to GQA while using the same number of KV heads, primarily by caching one tied state per head. For a setup with 8 kV heads and a tensor parallelism degree of 8, GTA8 stores 1.5 times the head dimension per token, with half of that coming from separate rope. In contrast, GQA8 stores double the head dimension, resulting in a minimum savings of 25%. When we use 8 kV heads with a tensor parallelism degree of 4, the difference increases, as GTA8 allocates 2.5 times the head dimension per token, while GQA8 uses 4 times the head dimension, showing that a moderate tensor parallelism degree offers more memory relief. In our GLA experiment, we used 2 latent heads to match the unsharded KV cache size of MLA, where GLA halves the KV cache per device when the tensor parallelism degree is 2, while MLA duplicates the cache across devices. Up to the 1.471 billion scale, the model quality remains similar. We plan to evaluate larger models with more latent heads while keeping the head dimension fixed at double the head dimension to further test GLA's performance. For instance, the Llama 4 models, which can have up to 400 billion parameters, use GQA8 with specific head dimensions, where the KV cache size per token for a tensor parallelism degree of 8 is double the head dimension, and beyond this degree, it duplicates the cache. A corresponding GLA8 with 8 latent heads would cache slightly more, at 2.5 times the head dimension per token, with half of that from decoupled rope. Whether GLA8 enhances quality compared to GQA8 with a similar cache budget remains an open question. From our 1.471 billion scale experiment, GLA2 achieves a validation perplexity of 10.218 compared to 10.202 for GQA4 on fine web edu. Additionally, the extra cache footprint from decoupled rope can be reduced by applying rope only in certain layers, as demonstrated by Cohere and Llama 4. We will address these scaling studies in future work. We also show that arithmetic intensity increases with the number of query heads. Our appendix includes an ablation study that replaces full query and output projections with low-rank versions to reduce parameters. This reduced capacity is balanced by increasing the column dimension to add more query heads per group in GQA and GTA. The goal of this ablation was to enhance quality or maintain it while further reducing the KV cache and improving arithmetic intensity, which boosts GPU utilization. The validation perplexity was slightly worse by 0.1 to 0.2 compared to the baselines when we tested fewer ranks and query heads. A detailed analysis of this trade-off will be part of our future work. Lastly, we aim to explore how parallelization and arithmetic intensity interact in other architectures, such as Mamba and linear attention, to better utilize modern hardware.